Hey, thanks a lot. Um, so, just a quick review. Last time I kind of laid out what the problem we're after, which is we want to use ideas from quantum scattering amplitudes to solve problems in gravitational wave physics, and I mean classical, standard gravitational wave physics that Riccardo Storani is talking about. And one thing I showed you last time in that homework is if you look at the 2-to-2 scattering amplitude, so it's just a simple diagram, and you Fourier transform it, it's the potential. So that immediately shows the connection between the classical physics and the quantum physics. It's like they're the same thing, except for a Fourier transform. Now, when you go to higher orders of perturbation theory, it's certainly true that quantum physics, let's say this diagram, there's quantum in here, which you have to remove from the problem. Now, I won't discuss this, but Radu Roybon is going to discuss this quite a bit. You have to get rid of quantum, so you take h bar goes to 0. And what that translates to is actually something very simple. In this diagram, there's a momentum, the graviton momenta. You have to take those small. H bar is going to scale with the graviton momenta. He's going to explain that in some detail. So what you do is you calculate this amplitude, but very early, before you actually do any integrals, you take this limit and you get much simpler integrals. So the classical physics is just around the corner. The quantum calculation and the quantum calculation contains the classical physics, and the soft expansion in the integrand, where the graviton momentum is small, it's basically a series expand, that's where the classical physics is hiding. Or not hiding, it's just there. Okay, so Radu is going to explain all that. What I will discuss is the machinery of how the modern way of doing scattering amplitudes at high loop orders. How do we do it, especially in theories of gravity? So it's a more general problem. You're interested in some gravitational scattering problem for whatever reason. Well, this is one example why you might be interested in, or maybe I've spent a lot of time on supergravity and trying to understand the renormalizability or non-renormalizability problem in gravity. And so you have to get to very high loops, and how do you do that? And that's the part that I'll explain. You could say the modern viewpoint of how we think about gravitational scattering. And so modern viewpoint for gravity and scattering. Okay? And there'll be some ingredients of how we go about this. One very important ingredient, because it greatly simplifies our understanding of how gravity interactions work, is something we call the double copy. And if you haven't seen this before, especially if you're a general relativist, you'll be very surprised. It's basically a statement that all the interactions of gravity are actually contained in Yang-Mills in the gauge theory, if you understand how to read it. It's basically, this name has to do with two copies. You know, spin 2 is like two spin 1s, like a product of spin 1s. That's a kind of naive statement about free gluons and free gravitons. But in fact, that idea, we'll see, carries to the entire S matrix, to all orders of perturbation theory. Okay? And that's, in fact, how we do all these calculations. We always use the double copy because it's just a much slicker and nicer way to be thinking about things, and tends to lead to much more compact expressions, especially as you're pushing up in perturbation theory higher and higher orders. The next thing which we'll discuss, is something called generalized unitarity. So you heard in Yaroslav's lectures, he was talking a lot about residues. Let's say you have like this, and he's talking about the going to the on-shell limit and using factorization analytic properties. And then the idea is through these on-shell recursion relations, you can build up all the tree amplitudes using what Yaroslav was discussing and will continue to explain. We're going to do the same, except those same ideas, we give it a different name. We call it generalized unitarity. That's basically, you're looking at residues simultaneously. That's maybe the way of thinking about it, what this generalized unitarity is. But it's the same basic principle applied to loop level. And it's something that you can do to arbitrarily high orders of perturbation theory. I mean, just to throw out a number, we've done 5 loop calculations in gravity and supergravity. And the methods, they don't have any, like something goes wrong, like there's a subtlety. It's straightforward once you see how to do it. Okay? Oh.
By generalized unitarity, you mean that you can write that scattering as the gluing
Yes.
more fundamental object?
Yes, yes. So absolutely, but there's some assembly. So back at tree level, if I was only thinking about this one residue at a time, I can't reconstruct the whole thing. I'd be missing some pieces. You have to look at all the channels to do a reconstruction, or use something very fancy like the BCFW recursion. And actually, I missed if Yaroslav already discussed that. Oh, okay, you don't know what those words mean. Okay, but anyway, you can do things much slicker and faster than just looking residues one by one. But the reconstruction comes from the information of looking at different channels. Okay, in the gravitational wave problem, it's a very happy problem because there's really just one channel you have to be looking at to do the reconstruction of all the pieces you're interested in. Okay? And then there's a third item, which I will not discuss, and neither will Radu, which is advanced integration. So when we use these methods, they allow us to build integrands. Like it's analogous to the Feynman diagrams without doing the integrals. But at the end, you have to do some integrals. And those integrals, well, at one loop, you definitely don't need advanced integration. And the school is not going beyond one loop. So we don't have to discuss it. But there's a very important, call it technology, that's been developed over the last 40 years for doing Feynman integrals at extremely high loop orders. It's the same technology we use to do 5-loop supergravity ultraviolet divergences. And this is, the source of this is from collider physics. In QCD, you need to go to high orders, electroweak theory, precision Higgs physics, you need 3 loops. And this technology of how to do this is now very well understood. If you're just beginning, it's actually very easy to use as long as you can read a manual. You download the software and it does the integrals. You know, there's some, and it's well explained exactly what you need to do. But that we won't discuss. But I'm pointing it out because, let's say in Radu's lecture, he's going to show you how to get the one-loop potential, so that it's basically the next correction to the thing I said, oh, it's the Fourier transform of this. He's going to talk about the next one, and he will do some integrals, but they'll be pretty simple. Anyway, he'll take care of that pretty easily. But then you may have a question: how do you get to the next level? You can't do the integration the way Radu is going to do it. And there's available technology. Okay? Now, let me just make a little preview of, so today I want to discuss the double copy, but first, let me just give a little preview. So you may have noticed something in Yaroslav's lectures. He said, if you look at Yang-Mills, and you're looking at the three-point amplitude, okay, so let's say we have 1, 2, 3. Okay, and then he wrote down, ignoring the color factor, which he's going to discuss color in today's lecture. So let's just ignore the color. He wrote down a formula, and of course he was very proud of the fact that this is the only thing you can write down for the interaction of gluons. So this is Yang-Mills, and he argued from the from the little group weight that this is the only thing in dimensional. And he had his arguments that this is the only thing you can write down. And then he wrote down something else, and he said, well, let's look at spin 2 massless. What is the only interaction you can write down? And he said, well, the only thing you can write down that has the right little group, it looked like this. Oh, and there's helicities. This is for one helicity configuration. 2 minus 3 plus. Same thing, minus 2 minus 3 plus. And he wrote down this thing. Three, 1. And then he squared this. Okay? And you might have been a little surprised by this. Yeah. Excuse me? Yeah. Oh, shit. Yes. Yes. I guess that's not what he wrote down. Yes. And I like writing it this way, even though it cancels. Yes. Thanks for fixing my typo there. Anyway, he wrote this thing down, and you may have been puzzled and said, gee, isn't that weird? This thing is the square of that thing. Now, say, that seems like a weird accident. But in fact, this is not an accident. This is the tip of an iceberg. Right? There's underwater, there's a lot more coming. So this is basically a statement that the vertex, it says that gravity, in some sense, it's like the product of, well, let me write it as gauge theory. Gauge theory. Times gauge theory. And so here's an example of, there's a squiggle here, so it's so far not precisely defined, but at least right here for the 3 vertices, well, they're not vertices, these are amplitudes, right? So these are gauge invariant objects. At least for these amplitudes, you can see exactly what those words mean, okay? And we'll see that, in fact, to all orders of perturbation theory, this idea, suitably defined, you have to, you have to order by order, you have to explain what you mean by this thing. But this basic idea is how we do gravity. So Einstein, no Einstein. Feynman, yes. We keep Feynman. So remember Feynman said massless, that gravity is mediated by massless spin 2. And then he explained how that connects to Einstein. And that's our starting point. We don't go to Einstein. We don't use field equations. The only thing we use is the idea that the gravity, this is gravity, is made out of spin 2 particles. And that's how Yaroslav derived this. These are spin 2, spin 1, and these are the only amplitudes you can write down, the only consistent amplitudes. Okay? And everything will follow. Everything we're going to talk about, high orders of perturbation theory. Well, you're not that high, but one loop, so it's the next correction to the tree. It'll all flow from the idea that a graviton is massless spin 2, a Yang-Mills is massless spin 1, and all the classical physics is going to come out of that. Okay? Everything. The entire theory of general relativity, order by order and perturbation theory for scattering, so all the nonlinear everything is included in my statement, to all orders of perturbation theory. If that wasn't true, it would be pretty useless, because then we couldn't do any high order calculations valid for LIGO, because something would be broken. You're missing, you're missing the detailed interactions. So the claim is the complete interactions of gravity are dictated, and we know how to use this. We know how to use this efficiently, dictated by its spin 2 particle, and also, as we'll see, this is what I'll lecture about today, is that the detailed dynamics, I mean, here there's a squiggle because I haven't defined what it is, but in detail, everything we need to know about the gravitational interactions for scattering, okay, for the S matrix, is obtained from gauge theory. There's no other information in gravity for the, perturbatively. Yeah. I'll show you how it's true. So this statement to any loop order becomes true through this. So if it's in the context of this generalized unitarity, the generalized unitarity, which I'm about to just give a little overview, the basic idea is that you can build the loops from the trees. So once something is true for the trees, it's automatically imported into the loops. Order by order, using on-shell data, everything on-shell. So you take tree amplitudes, you build loop amplitudes, and you can march order by order as far as you'd like. Okay. Nope. As far as, well, we haven't, if they exist, we haven't encountered anything. No pathologies. In a sense, this thing is designed, I mean, it can't fail in a certain sense, that the thing is designed, by its very construction, is to reproduce Feynman diagrams. So if we had a pathology of some kind, 10 loops, who knows what happens, that same issue would be there with Feynman diagrams. But, by construction, it has to match Feynman diagrams. Well, if we don't match Feynman diagrams, the problem is actually with the Feynman diagrams, because unitarity is more fundamental than Feynman diagrams. So we're just using basic principles that are built into the Feynman diagrams to construct the same answer you would have gotten from Feynman diagrams. Okay. Oh, yeah. Yes. Yes. Well, it was kind of valid, except those theories have their pathologies. The higher spin massless theories have pathologies. Mm-hmm. Sorry, I can't hear what you... Yeah.
Do I repeat all of it, or?
The last part, yeah.
So, yeah, the final question is if there is some other form of argument that is similar to double copy for spin that is not 2. So.
No, because well, if you try building, let's see, if the obvious thing, let's make a quadruple copy or something, try to build spin 4. But the problem is the object you get has pathologies, like spurious singularities or other problems. It's connected to the fact that, Yara mentioned this, that the consistent massless theories of different spins, you got your spin 1, and you got your spin 2, and then that's it, of at least the bosons. So you can try games, but the question is, do you get something that's actually correct? And you'll notice, I mean, the problems are going to come, they're going to come find you because you're going to try to build an S matrix. And the S matrix is required to have factorization properties in all channels. Everything has to work simultaneously. And the question is, can you find an object like that for higher spin? And the answer will be no. So in a sense, it's built into this formula. When you try to do it, you'll discover inconsistencies with unitarity, factorization properties. Yeah, but in any case, at least one good thing is, the key one we're interested in, of course, is gravity. And for gravity, everything is happy. Okay, and the other concept, so today's lecture, I'll focus on this, but the other idea is this generalized unitarity. And it's an idea that if you're interested in a loop computation, you can build the entire expression by looking at only on-shell data. When I put a line across here, these are physical. Okay, maybe they might be complex momenta, like Yaroslav was discussing, but in terms of gauge invariant, that they're completely gauge invariant, they're unique, they all make sense. There's a sewing procedure for building up, order by order, the entire S matrix. Now, this one channel is insufficient. In general, you have to look at multiple channels, and I'll show you an example of how to do that. A reconstruction of the complete amplitude. And this logic of how it works, why this procedure is going to work, is, in a sense, it's designed to reproduce Feynman diagrams. Like it's literally designed that it's supposed to give the same answers as we understand very well for Feynman diagrams. Okay, and I should mention this logic, well, I think I already said it a little earlier. The logic for doing this sewing, it's very similar to the type of logic that's used at tree level. It's a little bit different, but it's the same basic idea that the information for computing the S matrix for any number of legs or any number of loops, it's contained entirely in on-shell data, that you don't have to be thinking about off-shell quantities. Off-shell quantities are not physics. On-shell is physics, because off-shell is gauge non-invariant. So, okay, so everything is contained in terms of on-shell things, which is definitely the way it should be. Okay. Now, to explain the double copy, maybe the way to do it, the first way, maybe historically, where it was first observed, it came from string theory. Alpha prime goes to 0. Infinite string tension reduces to field theory. And you find a set of relationships between, so this is Kawhi, Llewellyn, and Tai in 1985. And what they observed, and I'm not going to go through this derivation because I would, I'd wander way off into string theory, and it would be many lectures would have to be given to explain how these formulas were originally derived. You're going to derive them the old-fashioned way by calculating both sides and see it's true, at least for low order. So that's not a proof, but at least you can check certain things. So the first one, we know it's true already. I want to put a tree here to keep on reminding you. So that we're just at tree level. So this is gravity. So the M, just to distinguish from a Yang-Mills, I'll call this M. This is gravity, tree amplitude. And I'll put 3 labels, skip the commas. So it's just the 3 legs. It's exactly this. So anyway, we can see our relation. Oh, maybe I lost a minus sign somewhere. But anyway, normalized normalized in some particular way. Okay. And the I here, I mean, what's the I doing there? Well, the I is because if I take a product of two tree amplitudes, there's an I square, so now I'm missing an I, so I'll just put it back. Also, I'm leaving out the coupling, so there's no coupling constant here. Right, this is stripped of the coupling because if I did put in the coupling, then I'd have to correct for the couplings because, you know, then it makes no sense because it's two completely different theories. This side is gauge, and this side is gravity. So this is the first relation. A more interesting relation is the next one, 1, 2, 3, 4. And that's equal to minus I S12 A4 1, 2, 3, 4 A4 1, 2, 4, 3. Okay. Now, what are exactly these things? You may ask what happened to the color. It's the first question. Because the color factors, you know, something is wrong. There shouldn't be color factors here. Well, indeed, these things are not complete amplitudes. They're called partial amplitudes. This is partial, and I'll define what that is. It's color stripped. That's another name you could say, or color ordered, let's call it. Today's lecture, I believe, color ordered comes in Trinka's lecture. So I won't explain too much about it and just say, wait for Trinka's lecture, but let me write down one formula which will explain what this thing is. So let's take the full amplitude including color. Where can I write? Well, let me put it over here. A4, 1, 2, 3, 4. So this is full color is equal to the sum over non-cyclic perms of trace of TA1. This is fundamental representation generator of the gauge group A2, A3, A4. It's convenient to use the fundamental representation generators. But at the end, anyway, when you add up all the pieces, it's adjoint representation, gluons. Gluons are adjoint representation, but I'm just writing it in terms of fundamental representation generator. The free index, you see, is adjoint representation. I hope you know what I'm talking about. If you don't know what I'm talking about, you should wait till Yaroslav's lecture. But there's a color factor here. That's the important. There's some color. There's another matrix that describes how the gluons are interacting. And then there's another piece. That's the one we're interested in. And that's a 4. This is, there we go. This is this guy. It has a characteristic that the legs have an ordering, 1, 2, 3, 4. So if we look at this side, and let's suppose I swap 4 and 3, what happened? So I take two gluons and I swap them. What are gluons? Gluons are bosons. Same thing, right? But in this color stripped amplitude, so that's swapping. The Bose symmetry requires also that you're swapping color labels. But on this side, once I've taken off the color, it no longer has Bose symmetry. This thing, if I swap two legs, it's a different object. Okay? The swap there is it. So that's what this is. And in terms of Feynman diagrams, what this object is, it's the set of. It comes from the set of diagrams. Like I'll write down. Let's see. A 1, 2, 3, 4. 1, 2, 3, 4. So I write down diagrams. and there's only 2 of them. 1, 2, 3, 4. See? Legs 1, 2, 3, 4. Right? The other guy, 4, 3, I have to swap. It's only these 2. These are the only 2 diagrams that I can write in a planar way on the plane, not this. I'm not supposed to swap anything like that. That one is not part of the list of these color ordered. I mean, the ordering refers, there's an ordering of legs. Okay, so it's a piece. Anyway, this thing, this A1, 2, 3, 4, it's a piece that you can extract out of the Yang-Mills amplitude in a well-defined way. And basically by stripping off the color, organizing them in a certain way. This thing is gauge invariant. And you can argue that's gauge invariant because these traces for sufficiently large representation, like SUN, n goes to infinity, all of these things have to be independent. So that argues that these things are gauge invariant. Okay, and that defines, it's this formula. If you take the Yang-Mills amplitude, you write it in this format, you read these off, that's what goes into this relationship between gravity, there's gravity, and this is gauge theory, right? And it's remarkably simple, yeah? We don't have it because it would contribute to a different color trace. So the ordering 1, 2, 3, 4, you'll find if you work out the color factor of the diagrams, you'll find that the U-channel guy does not contribute to this particular color trace. It appears in a different color trace. Okay. So I didn't actually explain. I mean, your question was a good one. I didn't explain exactly how this is done and where this comes from, because I'm going to defer to Yaroslav, who will explain it. But all I need is that there's some object that you can do some color reorganization. This is called a color decomposition, and you extract that out of Yang-Mills. And that is the object that goes in here. It's well defined, it's gauge invariant. In fact, Yaroslav already wrote them down. Maybe he didn't call it that, but remember he wrote down something that looked like this. Maybe minus, minus, plus, plus, and he said Park-Taylor, 1, 2, 2, 3, 3, 4, and then 4, 1. Whoops. And if you look carefully here, so he wrote this, right? You recognize, he was actually writing down one of these color-ordered amplitudes. And you may actually notice, related to that question, there's no U-channel pole here. So where did the U-channel pole go? It winds up in a different color ordering. Okay. Now, this thing continues. In fact, it continues for arbitrary number of legs. Let me just write down, just so you can see what it looks like at a higher number of legs. So this one is particularly simple because you see it factorizes. See, gravity is a product of gauge theory, right, directly. Let's look at the higher ones. So let's look at the 5-point. One, 2, 3, 4, 5 is IS120. I think, well, even though I probably didn't define it, I think you knew what I meant because Yaroslav was doing this. So S12 is just defined to be P1 plus P2 squared. S34 A 1, 2, 3, 4, 5. I should maybe tree. Maybe I'll stop writing tree. Okay, I'll stop writing tree. I'll stop putting the label 5 there. A21435 plus I S13 S24 A13245 A31425. Okay? And there's a regular, like a formula you can write for any number of legs, etc. Any n, any number of gravitons. And this basic trickery, it works also when you put matter in. I'm not going to explain that, but it's something that works very generally. Gravitons. Okay. Now you may notice maybe there's a squiggle here. So you'll notice the product. Well, maybe in this formula we should change the slogan slightly. It's a sum of products, but close enough, right? It's still built out of products, and then you have to add it up in a certain combination. The proof of this is not so simple. This one, where was it on this side? This one you can prove. Yaroslav gave you the power, right? He was writing down gravitational amplitudes. He was writing down Yang-Mills, or there it is, the Park-Taylor, right? So you can go home and check it. That sounds like a good homework assignment. So at least you can prove it at this level. Now, later on, I'm going to use something related to this. It's actually closely related. There's some hidden relations inside Yang-Mills alone, and they're closely connected to this relationship to gravity. Let me write down some relations. They're a set of amplitude identities related. Let me just write down one of them. 1243 is equal to S23 over S24 A1234. Now, okay, this one is really not a big deal because, see, you have the amplitudes, right? You have the amplitudes, you can relabel them, and then you can check that this thing is true, right? It's very straight. Anyway, so that'll be an obvious, simple homework that I can give you, just to double check this. So this formula we will need later when we talk about gravitational waves, because we're going to use that to turn an electrodynamics problem into a gravitational problem. It's basically use the double copy, but then arrange it in just the right way, so it's very simple. Okay. This one we can say proof by homework. And there's an infinite number of these relations, very analogous to these Kawhi-Lowell and tie relations. Okay. Now, maybe one comment about this. On this side of the formula, if you look at that Park-Taylor, there's a set of singularities. You'll find it in the 1-2 channel. You'll find it in the 2-4 channel. Here, you find poles in the 1-2 channel and the 2-3 channel. So how can these be related? Well, the answer is this corrects for it. This side has a 1 over S24 pole, so I put it in, and I take out the pole I don't want. And that's why the formula looks like that. But like I say, you can confirm it using just Park-Taylor. Okay. Now, there's a different way of thinking about the same problem that's actually much slicker and cuter, which is we can find in in terms of a diagrammatic representation, how to convert a gauge theory amplitude into gravity. Okay, and this is called the color kinematics. When we do the high loop calculations, that's the version we prefer, because the Kawhi-Llewellyn tie representation, this thing, it doesn't respect, it doesn't play nicely with diagrams. Diagrams get all kind of messed up. And when we do integrals, we need diagrams. So this is not the best way to do it, because you lose the diagram representation, which you then have to repair before you can do integrals. So it's for some very technical reason that we actually prefer the second way. Okay? And let me show you the second way. I'll come over here. So what I want to do to get started, I want to write the amplitude in some schematic form as a sum over cubic diagrams. By cubic diagrams, I just mean diagrams that only have cubic vertices. And I want a color factor. This is color. So this is a sum over the number of diagrams of cubic diagrams. So this is color. Then there's some kinematics. So depends on P and polarizations, polarization vectors. Okay, and then there needs to be a set of propagators, like a product. Okay, it's massless. Let me write it as like, okay, so it's all the propagators, some diagram, and it has some number of, I need another label. So for diagram I have a bunch of propagators, and I have to multiply out all the propagators. So these are the propagators. So for any given diagram, let's just fix this. For any given diagram, I can read off the any cubic diagram like this. I can read off the propagators. If this is 1 and 2, this thing is 1 over S1, 2, and then maybe this one, well, this one here would be the 3, 4, 5. This one here, that would be an S4, 5, 1 over that. And then over here, I need 1 over, let's call it S4, 5, 6. That means I sum the momenta 4, 5, 6, and then I square it. Okay, that's this. So the propagators, you can just read off straightforwardly from the diagrams. The color factors, it's the same story. You saw Yaroslav, he said, well, I'll just pick something simple. Let's do it here. My favorite one is 4 points. So I would put here F, A1, A2, E. I think even use the letter E. And then on this one, I put an F, A3, A4, E. And these are the color matrices, right? And I have to sew them together. And by doing that, that tells me what the color is for any diagram. And for any arbitrarily large diagram, I just can figure out the color by looking at the diagram. There's a one-to-one correspondence between a diagram and the color factor. And then the numerator factor, that's more complicated. Maybe I need some Feynman rules, or maybe I need something fancier, some modern way of getting this kinematic numerator. So this thing is harder, but every diagram has some kinematic numerator that you work out either by Feynman rules or some other way. Okay? And maybe just at, so these types of diagrams that I'm talking about at the, at the 4 point, there's 3 of them. At the 5 point, there are 15. And there's a simple formula, 2n minus, I shouldn't use the letter n because n is like a numerator, but let's make it m, like an m-point function, minus 5, double factorial. A double factorial, let's say what that means is you take 5 times 3 times 1, so that's the double factorial, skip the even ones, and that tells you the number of diagrams that you have. Okay. Now, first thing to understand is you may raise your hand and say, what happened to the 4-point interaction? We all know that a Yang-Mills Feynman rule, where did that, that's hiding there. We all know that, well, let's look at 4 points. So let's follow the Feynman rules. So there's 4 points, and we're going to do it Feynman. I hope Yaroslav is not here to see me use Feynman rules, but it's only 4 points, so maybe he'd forgive me. So we would write down, and you can use Feynman rules as well for 4 point. It's not a big deal really. Yeah. So we would write down, diagrams like this. 1, 2, 3, 4. Let me actually draw them all the same way and just relabel them. Okay. Let me just write it out. Oops, I meant the contact term. Say, like this, and okay, there's a 4-point contact term. This diagram is not in that form. By cubic, I mean only 3-point vertices. This has a 4-point, but not a problem because I look at this diagram, and inside this diagram, if you open up a Peskin and Schroeder and you look at the vertex, you'll find that, let me put some labels here, sorry. 1, well, let's make this 2, 3, 1, 4. Let's keep 4 there. And then 3, 1, 2, 1, 2, 3, 4. Okay, so those are the 4 Feynman diagrams we would write down. Okay, and inside this Feynman diagram, you'll discover there's one term that looks like this. A1, A2, E, F, A3, A4, E, inside here. So there'll be 3 color factors. This is one of them. So you look at this thing and you say, oh, this is just like the color of this one, but it's missing my 1 over S. So inside this diagram, there'll be a piece that looks like this, right? But it doesn't look like this diagram because the propagator is missing. So how do I put back the propagator? Well, there's this fantastic identity. I think you guys know this. You see, if you take this, S over S, that's 1, so I can put that in. And now I have a propagator. This belongs in the numerator. Right? So this formula, this one, I said, oh, it looks like this. It's only the cubic diagrams, cubic vertices. But then you say, look, Feynman diagrams don't do that. But that's okay. I can immediately correct it. I find a color factor that looks like a certain diagram. And then I multiply and divide by the appropriate propagator that's missing. And once I've done that, I automatically have wound up in this format. I just got rid of the 4-point diagram by basically expanding it out. It goes like S times this diagram. So 1, 2, 3, 4. So the S12. Oh, let's make this S12. S is, yeah. Anyway, I slipped in an S there because usually S would be S12 would be the normal way of writing it. But this thing just cancels the propagator. You recover the 4-point contact term, but you now assign it to this diagram. So that's kind of trivial. Now, as some homework assignment, I'm full of homework today, what you can do is work this out. That's the homework. You can use Feynman diagrams. We'll go over that. Let me tell you what the answer is. It's a little bit complicated, but I think it's actually good to write down. So I'm not going to use helicity. But there's some reason why I don't want to use helicity. So I'll just do it in terms of formal polarization. So I'm, in fact, taking a negative step compared to Yaroslav's lecture. He's fancier. He's using helicity states, which are better. But this is a simple enough problem that we don't need any fancy stuff. Just do it as close to the textbook way as we can. I think that might be more enlightening. So we'll call it, well, let's take S12 equals S. So I don't have to write these things. T, S13 equals U, ST and U. So what is this numerator now of the S-channel diagram once I've absorbed that contact term? And if you go home and do the algebra, I actually want to write it all out because you'll see something very surprising. Plus 2 epsilon 1 dot P2 epsilon 2 mu minus 1 goes to 2. It's slightly lengthy, but if you write it in a slick enough way, it's not too bad. Okay, then there's another factor that's multiplied, epsilon 3 dot epsilon 4, P3 mu plus 2 epsilon 3 dot P4 epsilon 4 mu, and then minus, and it's 3 goes to 4. And then one more term, and this is the piece that came out of that contact term, that 4-point contact. So there's, the S came from multiplying and dividing. Okay, and then epsilon 1 dot epsilon 3, epsilon 2 dot epsilon 4, minus epsilon 1 dot epsilon 4, epsilon 2 dot epsilon 3. Okay? And then the other diagrams, if you work out one diagram, you don't have to work out the other diagrams because they're the same thing except the labels are different, right? So just relabel it. So CT times NT is equal to CS times NS. That's the numerator and the color factor. But I'm supposed to swap 1 goes to 2, goes to 3, goes to 1. And then for the U, it's the same thing. CS, NS, and then I relabel it differently. 1, 3 goes to 2, 1 goes to 3, goes to 2, goes to 1. Okay, and that's the whole amplitude now written out in this format, only cubic diagrams, right? There's, let me actually write it explicitly, what we've done. Okay. Oh, I see I'm running short of time, but I think I'll get to my punchline at least. We have that the amplitude, this is now the full amplitude. A is equal to the sum over, call it S, T, and U diagram. So there's 3 diagrams. Well, maybe I equals 1 to 3, or I don't know. Let's call it I I equals STU. How about that notation? It's NS CS divided by the propagators. You know, call it capital P with an S. With a, I guess, well, sorry, I. So I is S, it's T, or it's U, right? So this is the numerator in the S channel, what I wrote down there. This is the color factor in the S channel for the first term, and that's the propagator, which is, of course, just PS is, of course, equal to S, and so forth. Okay? Now, this is where the funny thing happens, is these color factors, they satisfy an identity. And that identity, Yaroslav happened to mention. He said the Jacobi identity. Right, you remember that? And he said that the color factors of these three diagrams, if you add them up, he might have had different signs because it depends how you orient, you know, how you label things. But at the end, whatever he wrote, it's the same identity if you align labels. CS plus CU plus CT equals 0. And this is a consequence of an underlying, there's a Lie algebra underlying this. Which is where this identity came from, and as Yaroslav explained, if it's not a Lie algebra, the amplitudes would be inconsistent. The color factors have to satisfy this. So there will be another homework assignment. Well, first homework, go work this out, you know, show that I did it correctly. And then the next thing you should do is you should add this up, NS plus NU plus NT. Whoops, just add it up. And what you're going to find is that this is equal to 0. So these numerators, in this 4-point case, at least, they satisfy the same Jacobi identity. Now, you're probably thinking, oh, that's pretty weird. What does it mean? Why should I care? Well, that we will get to. So, for the case of 4 points, it turns out that it does not matter at all how you do this. You can work in light cone gauge, for example. You can do whatever, any gauge you like. Makes no difference. But you have to put these on shell. Remember, on shell good, off shell bad. Off shell you won't see anything. Right? On shell is the only place this works. This is for, it has to be something physical. It has to be something gauge invariant. Right? But in any gauge, I mean, the amplitude, of course, is a gauge invariant quantity if you add up all the pieces. And at 4 points, where it's very simple, it turns out that the details of exactly how you organize things, as long as the amplitude is correct, you have to have a correct amplitude, you'll find this to be true. And now, I'm not going to prove this, but I will claim this, and there are many proofs in the literature that, in fact, this is true in general. In fact, one can find a organization, let's call it, such that for any number of legs, so this is trees, let's talk about trees, such that if I have a Jacobi identity that relates 3 diagrams, CK, so these are 3 diagrams That's what the labels are. There's 3 diagrams. And it could be at endpoint, arbitrary numbers of legs, but you pick 3 diagrams and you find that the color factors are related through a Jacobi identity. Then there exists Ni plus Nj plus Nk is equal to 0. We call this color kinematics duality. This is color duality. The proofs are generally very opaque, but I have something better than a proof. I have a computer program that you can download that tells you these numerators. So that's your proof. You just download it, and then you can verify that those objects have the right property. Here's a paper. It's 2005.03638. And there's many versions of this. This is not the only one where you can actually get the explicit form of the numerators that satisfy this. So at 4 points, whatever you do, as long as it's correct, you'll find this to be true. At higher points, you have to beat it into the right format. And now well, like I say, you just download a program and it tells you any number of legs, how that works. Now, you say, okay, this is very amusing as entertainment for the morning, that there's some funny thing happening between color and kinematics. There's some unusual, strange thing. Now, what's it good for? That's the fun part. So there's a next claim related to Kawhi, Llewellyn, and Tai. This is now a much cleaner form of what I showed you before. So let's say I did this, that I put it into this form, and let's suppose that Ci plus Cj for every single color factor where there's a Jacobi identity. It's the list of all Jacobi identities. So of course this thing works. And there's a one-to-one correspondence that for every one of these, I have that this is true. Okay. Then the claim, which is again proven, is if I want to start, I start with Yang-Mills, and I want to go, or let's make this gauge theory, gauge, and I want to go to gravity, and I want to go to gravity. What I do is I take Ci and I replace it to Ni, just like that. This Ni is the Ni of Yang-Mills. So gravity, let's put an M, so this is now gravity. Is equal to the sum over the cubic diagrams of Ni over, what did I write there? The product of the, well, it's the product of all the propagators of the diagram, pi alpha square. Okay? Magic. In a sense, it's actually true magic, because this is not fully understood. You might think if every numerator satisfies a Jacobi identity, underlying it is some infinite dimensional Lie algebra. Some things are understood about this Lie algebra that you think exists, but not everything. It's still not completely understood. But this is proven at tree level. Once again, I'm afraid I can't show you the proof because the proofs are pretty opaque. I don't know of a proof that's really slick. Or, I mean, there are ways of understanding it that are relatively slick, but it needs a whole machinery to be set up in order to interpret this. Now, there's a little generalization, which is that the two theories don't have to be the same. So there's two copies, double copy. One copy might be, for argument's sake, n equals 1 super Yang-Mills copy. The other copy might be n equals 4 super Yang-Mills. It's a different theory. Maybe it has matter, maybe it doesn't have matter. And depending on what these theories are, where this came from, you get different gravity theories. And the way to know what's what is pretty simple. You just have to inspect 3-point interactions, and as long as you're minimally coupled, you know exactly what theory it is, exactly the mapping between the gauge theory and the gravity. Okay. So I think I'm now officially over time a little. What's that? Oh, I have. But that included questions, or? Okay. Okay, let's see. I lost my. Okay, maybe I can tell you one more thing. Oh, haha, yes. I can tell you one more thing. Little arithmetic. So there we have it. Graviton, in a very specific way, gravitons are double copies of gluons, and not just in some superficial way, like free gluons, free gravitons. That's trivial. That's not interesting, right? The full interacting theory. This is the S matrix with any number of legs, not loops yet. We'll get to loops later, but at least a tree level, to any number of legs, this is a statement. Gravitons are 2 copies of gluons in a very specific construction. Okay? But if you're good with arithmetic, you may notice something funny. Yeah? No, it does not rely on the number of dimensions at all. And that's actually very important for technical reasons. As we do, let's say we're going to do the gravitational wave calculations, we have to use dimensional regularization. Right? So you'd run into all sorts of issues if this was not compatible with dimensional regularization. Yeah. Well, I'm sorry. Yes. Yes. Okay, so this construction is entirely in flat space. There ain't no cosmological constant in this construction, okay? So it's relevant, at the end, this construction will be relevant for problems where you have an asymptotic flat space. Otherwise, you have to re-examine exactly what you've done, okay? Oh. Yeah. Oh, yes, sir. Masses, well, if...
Massive gluons. Massive Young's field.
Yes. So massive theories are very happy because of sorry, so the question was about massive, but I didn't hear. Anyway, how do you do masses? Maybe that's the way of phrasing the question. So it turns out, luck is shining on us, and the luck comes from the fact that this is valid in d dimensions. So immediately, under a dimensional reduction, which will generate masses, this is going to work. And in fact, you could say that's how, in fact, we do the, construct the massive amplitudes that we need for the gravitational wave problem by using dimensional reduction. Okay. Yeah. What's that?
Last question about the unitarity constraints if you consider an Euclidean quantum gravity.
Well,
is there something equivalent to these unitarity constraints on the Euclidean case?
how about this? I don't want to get into this. So if we're working perturbatively, order by order in perturbation theory, there's no confusion. Euclidean, you know, we understand, like Feynman diagram, we understand very well how to analytically continue between, you know, it's just the wick rotation and things like that. And all of that is built into it and very straightforwardly. And so I think the way you should think about this construction is you should be thinking of this as an effective field theory describing the propagation, or how do gravitons in flat space, how do they interact? And you want all the interactions. So it's a construction, you could say a flat space construction, and no, you know, no weird, and it's one-to-one mapped. Any question you ask me about gravity, I can immediately turn it into a question about Yang-Mills.
I agree with
Yeah.
you that for the gravity, at the Planck level, there is no geometry, there's no fluid, there's only gravity.
Yeah. Only gravity. And this is, well, yeah, very high, and it turns out that the problem of the interaction of two bodies can be entirely phrased in this language.
So I have a question also. If I understood correctly, for each pairing of gauge theories, we have a different kind,
Yes.
a different theory of gravity. Is there a way of, like, we know a theory of gravity? Do we know how to choose the gluonic theories so that we get the right theory of gravity we are trying to understand?
Yeah. So, well, in simple cases, it's very straightforward. Like if you're interested in pure gravity, like say with a scalar, and I'll explain exactly how to do that. Okay. Let's say the pure supergravities, it's all very trivial because basically you just have to count the states, and then you know basically you know exactly what's going on. So in simple cases, it's completely obvious. Simple counting on states. And then if you need a little more information, you inspect the three-point vertices. And if you're in a minimally coupled gravity theory, those three-point interactions are all you need to then understand the entire theory.
Okay.
Yeah.
What do you mean by a different theory of gravity? We have an extra, I don't know, an extra scalar field or extra dimensions,
Well,
or
well,
can
for
be
example, like here would be a simple example. Suppose I'm interested in the case of a Schwarzschild black hole. So I would design something that in this construction, I wind up with a scalar, which then is my Schwarzschild black hole. But suppose I was interested in a Kerr black hole, I'd have to pick a different theory, a different gauge theory, one that includes spin, in order to properly model the Kerr black hole. So, you know, it's fairly straightforward. Let's say I know I want a certain theory. Let's suppose I wanted n equals 5 supergravity, or maybe it's n equals 4 supergravity with a set of matter multiplets. I just design the thing. It's like, okay, let's see, matter multiplets, you know, how many states are there, and I do some counting, and then I figure out, well, I better have let's say it's n equals 4 supergravity. You know, maybe I could build this out of using two n equals 2 super Yang-Mills, you know, and so on and so on. And then I just adjust all the multiplets to be the right. So it's actually quite straightforward once you know the rules. It's actually quite remarkable. It's that simple. You'd think it would somehow be very complicated, that gravity is very different in some way. I mean, just look at the Lagrangians. You think it's very different, but it's not. Let's see.
So any other questions? Okay.
Is there more questions? Or I wanted to actually point out there's something funny about what I just said.
So
Although I don't know if I'll have time to fix
maybe
it.
you want to wrap up before? And
Yeah, well, maybe the little wrap-up is there's something funny about what I said. If you're paying very close attention, you'll notice that there's something funny right here. So let's look at pure Yang-Mills. So you heard Yaroslav's lectures. Let's see, how many states for Yang-Mills? Oh, there's a plus helicity, there's a minus helicity. And then Yaroslav was talking about gravity, and he said, how many states? Plus helicity, plus 2, and minus helicity. So it's 2 states. Last I checked, if I take Yang-Mills times Yang-Mills, equals gravity, something like that, or goes to gravity. Let's see, 2 times 2, wait a second, is not equal to 2. So there's something wrong here. So this construction has extra states in it. So I think maybe I'll begin the next lecture by explaining why those extra states are not a problem. So suppose I'm interested in 2 black holes that are interacting. Oh, sorry, maybe I should name those states. Those extra states have a name, antisymmetric tensor or axion, and dilaton. So there's 2 extra states. Last I checked, in our universe, maybe another universe is different, you don't want those extra states. So if you do this double copy, it looks like you got a serious problem that you have too many states, right? Because the double copy, you have the dilaton in there, and the dilaton is going to just couple to those black holes, and then you're going to get the dynamics. You'll figure out a Hamiltonian, sure, but it'll be the wrong Hamiltonian. It's the Hamiltonian of another universe. So you have to remove those states. So that sounds really bad. Oh, you need projectors, but it turns out, and that's what I'll show you next time, is this generalized unitarity is our friend. Because every time you cut a line, this will be the punchline. So there's some problem about projection of states that the control, it's related to the control of the theory. How do you know what you want? So I want pure Einstein gravity, and I want it valid to all loop orders and so on, right? So how do I control that? How do I do that? Because the double copy inherently gives you the wrong number of states, because 2 times 2 is 4 and not 2. But if we look at a unitarity cut, in this cut, when we sew them together, we stop the dilaton. We just, right in here, we just, it's very straightforward to either do an helicity formalism and just toss it out with no work at all, or a little bit of work. You put in a physical state projector, and if you do it right, it's not a big deal. And I'll explain how to do that next time.
So let's thank Zvi for his lecture.